Assalamu alaikum. We are going to discuss Diffie Hellman key exchange in this video. So imagine we are in the same model of communication. So Alice is sending a message to Bob. So when Alice will be sending a message to Bob, he will be sending the message through a communication channel. So we assume that this communication channel is compromised. That means a hacker, Evil Eve, is sitting on the communication channel, or she is capturing the packets, so which breaches the confidentiality. That means if any message M is being sent over the wire from Alice to Bob, so this message M will be transmitted over the wire. So copy of this message will be sent to Bob and will be sent to Alice as well. So Alice will receive a copy of the message. So we see that the release of message content is here. So that means so release of message content means the confidentiality is lost, as we have seen in the book. So communication is not confidential anymore. So in order to achieve secrecy or confidentiality, we encrypt the communication with an encryption function. So if we write it like this, encryption is a function, enc is a function which takes two different inputs, which is the original message is taken as the input M, and it takes a key as the input. So this key must remain a secret and it produce a ciphertext C. So ciphertext C. So here the message M is the confidential message. We encrypt the message with the help of a key. This key must be must remain secret. So if this key is known, the game is over. That means Kirchhoff's principle says that the secrecy of the communication will remain on the secrecy of the secret key, will depend on the secrecy of the secret key. So if this secret key is known, hacker will be able to decrypt. So for this, we will be using a decryption operation. So decryption is another function which is the reverse of the encryption function. So we write the decryption function. So it will likely to produce the original message from the ciphertext. So decryption function, we understand that it will take input C as the input, so ciphertext as the input, and again it will take the key as another input. So with the combination of C and the ciphertext and the key, so this operation will produce the message M. So this operation will be M, and this key will be used to decrypt the ciphertext C. So this ciphertext C is being decrypted by using this decryption function. So encryption and decryption, these are two opposite functions. These two one produce a ciphertext, the other produce a plain text. So Alice will perform the encryption operation from her side. So before sending the message, instead of sending the message in plain text, she will encrypt the message with the key, this key, and producing a ciphertext C. So instead of sending the message like earlier in plain text, she will send the ciphertext C this time instead of sending the message M. So let us send the ciphertext C, and just like before, this ciphertext C will be received by the hacker as well as the Bob. So hacker and Bob and everyone knows the ciphertext right now, but Bob will be able to perform the decryption operation because she will receive the ciphertext C from the received message, and Bob already knows the key. So this ciphertext C will be given to the decryption function, and this will produce the plain text message M. But Evil Eve will not be able to perform this decryption operation because this key will not be known. So as long as Kirchhoff's principle is true, that means this secret key is being remain secret. So the message confidentiality will also remain there. So that means the message will remain a secret. So Evil Eve will not be able to decrypt the message. So this is a basic encryption and decryption operation. Now we see that there is something called key. So this is that key. So this key must be known by the both parties. So if both parties do not know the key, then encryption and decryption will not be possible. But the Evil Eve must not know the key, because the decryption will take place, and the ciphertext can be decrypted to get the original message. We don't want that. Kirchhoff's principle will be violated. Then how can we we establish this key
So
in
one
between?
idea
So
is
one
to send
idea
the
is
key
to send the
over the
key
wire.
over
So
the
if we
wire.
send the
So
key
if we
over the
send the
wire,
key
we
over the wire,
understand that
we
this key will
understand
no
that this
longer
key
remain
will no
secret.
longer
So
remain
this
secret.
key can
So
be
this
used
key
by the
can be
hacker.
used by
So
the
we
hacker.
cannot do that.
So we cannot do that.
So another way
So
is called
another way is called
they can meet
they
in
can
offline,
meet
or they
in
can meet
offline, or
in a
they can
secret
meet
place,
in a
so
secret
that they
place,
can agree
so
on a
that they
key
can agree on
that
a
we
key
will use
that
this
we
key
will
from now
use
on.
this key
So
from
they
now
will
on.
agree
So
on
they
a
will
key.
agree on a
Then
key.
they will use the
Then
same
they
key.
will
They will
use the
depart
same key.
and
They
they
will
will
depart
use
and
the
they
same
will
key
use the
to
same key
communicate
to
later on.
communicate later
But
on.
what if they do not
But
have
what if they
any
do not have
way
any
to any
way
chance
to
to
or any
meet
chance
with each
to
other?
meet
Imagine
with
these
each
two
other?
are two
Imagine these two are two
non-trusting parties. They have
non-trusting
no
parties.
chance
They
of
have
meeting
no chance
together,
of meeting
or
together,
there is the
or there is
communication
or the
channel is always
communication
being
channel is
monitored
always
by
being
evil eve.
monitored by evil
So
eve.
to solve this
So
problem,
to solve this problem,
we have the
we
Diffie-Hellman
have
key
the
exchange.
Diffie-Hellman key
So in the
exchange. So
Diffie-Hellman key
in the
exchange
Diffie-Hellman key
operation or
exchange
key exchange
operation or
algorithm,
key
it is
exchange
also known
algorithm,
as
it is
key
also known as
agreement.
key
It
agreement.
is the purpose of
It
this
is the
algorithm
purpose of
is
this
to
algorithm
solve
is
this
to
problem we have
solve this
discussed till
problem we
now.
have
So
discussed till
when
now.
a
So when
hacker
a
is sitting on the
hacker is
communication
sitting on the
channel and our
communication channel
communication
and
is
our communication
not
is not
encrypted, that means our
encrypted, that
communication is
means our
being monitored,
communication is
we
being
can
monitored,
still
we can still
establish a secret key
establish a
between these
secret
two
key
parties.
between these two
So how
parties.
this
So
is the
how
gist
this
of the
is the
algorithm. So
gist of the
imagine
algorithm. So imagine
you have Alice and Bob.
Alice
So
and Bob.
Alice has a
So
secret
Alice
number
has a
which is
secret
3,
number
Bob
which
has a
is 3,
secret number
Bob has
which
a
is
secret
6,
number which is
and there are
6,
two more
and there are
numbers which
two
is
more
defined by
numbers
the
which is
protocol.
defined
So
by
that
the
means
protocol.
everyone
So
will
that
know
means
the
everyone will
values
know
of
the
the n
values
and
of
the g
the
values.
N and the
So
G
what we
values.
are trying
So
to
what
say
we are
that
trying to say that
Alice and Bob,
Alice
everyone
and
should
Bob,
know
everyone should
the
know
values of
the
values of n,
values of
g,
N,
and
G,
Evil
and
Eve should also
Evil
know the
Eve should
values of
also know
n
the
and
values of
g.
N
So here
and G.
n and
So
g are
here
two
N
large
and G
prime
are two
numbers. These
large prime
numbers
numbers.
needs to
These
be
numbers
very
needs to be
large
very large
for these things to
for
work.
these things to
So
work.
let us
So
imagine
let
11
us
and 7
imagine
are very
11 and
large
7 are
numbers.
very
So
large numbers.
11 and
So
7
11
are
and
known by
7
everyone.
are
This
known by
11
everyone.
is
This
known as the
11 is
modulus,
known as the
and G
modulus,
is known
and
as
G
the
is known as the G is
generator.
known as
So
generator. So
Alice will
Alice
raise
will
the
raise
generator
the
to
generator
her secret
to
number.
her
So
secret
it will
number.
be g to
So
the
it
power
will be
x,
g to
then
the power
modulus
x,
of
then
n mod
modulus
n,
of n
and
mod
Bob will
n,
do the same,
and
g
Bob
to the
will do
power
the
y
same, g
mod
to the
n.
power y
So from
mod
the
n.
given values,
So
we
from the
see that
given
7 to
values,
the
we
power
see that
3 mod
7 to the
11
power
is
3
2,
mod
and
11 is
7 to
2,
the power
and
6 mod
7 to the
11
power
is
6
4.
mod 11
Now
is
these
4.
two numbers are
Now these
called
two
a
numbers
and
are
b, a
called
for
A
Alice and
and
b
B,
for
A for
Bob.
Alice and B
Now
for
these
Bob.
two numbers are
Now these two
exchanged.
numbers are
Whenever a
exchanged.
number is
So whenever a
exchanged, we
number
have
is
to assume
exchanged,
that
we have to
evil
assume
eve
that
knows the
evil
values.
Eve
So
knows the values.
a
So
and b, these
A
two
and
numbers are
B, these two
exchanged.
numbers are
Now
exchanged.
evil eve knows
Now
that
Evil Eve
the
knows
Bob's
that
number is
the
4
Bob's
and
number is
Alice's
4
number
and
is 2,
Alice's number
but
is
this
2,
doesn't
but
mean
this
anything,
doesn't
because
mean
in the
anything
next
because
step,
in the
Alice
next
will
step, Alice
raise
will
Bob's
raise
number, that means the
Bob's
number
number,
she
that
received
means the
from
number
Bob,
she received
to the
from Bob,
secret number
to the
she
secret number
determined
she
earlier. So b
determined
to the
earlier.
power
So
x
b
mod
to the
n,
power x mod
and
n.
Bob will do the
And
same.
Bob will do the same.
He received the number
He received the
from
number
Alice, and
from
he will
Alice,
raise it
and he
to
will raise it
his
to
secret
his
number's power
secret number's
and do
power
the mod.
and do the
Then
mod.
after that we
Then
will have
after that,
two
we will
numbers,
have
and these
two
two will
numbers,
be
and these two
identical
will be
as per
identical
this
as per
algorithm,
this
the K1
algorithm,
and
the
K2.
K1
So
and
without
K2.
even
So
meeting, and
without
even
even
in the
meeting, and
presence of a
even in
hacker,
the presence of a
they
hacker,
have
they have
successfully came up with
successfully
the same
came up
number.
with the same
So this
number.
is why you call
So
it
this is why you
Diffie-Hellman
call
key
it
agreement or
Diffie-Hellman
key
key agreement
exchange.
or key
Actually,
exchange.
key was not
Actually, key
exchanged,
was not
but key was
exchanged,
agreed
but
upon
key was
without
agreed
even
upon without even
exchanging any secret
exchanging any
information.
secret
So we
information.
did not
So
exchange
we
any
did not
secret
exchange any
information, yet
secret
a secret has
information,
been
yet a secret
established
has been
over here.
established
So
over
how
here.
this thing
So
is
how this
worked?
thing
So
is
let
worked?
us see
So
an
let us
example
see an
first.
example first.
So imagine we
So
have
imagine
Alice
we have
and Bob.
Alice and Bob.
So Alice and Bob
So
know
Alice
their
and
secret
Bob have their secret numbers as X and Y. So I deliberately took some large numbers. Let's see if we can do it. So everyone knows the two numbers N and G. The modulus is, let's take 13, and G generator is, let's take let's say prime number 17. Okay, so these two needs to be prime numbers, very large prime numbers. So now N and G are known by everybody. So N and G, these values are known by everyone. So Alice and Bob and Eve and everyone knows the values of N and G. So it's time to do the Diffie-Hellman key exchange. So for now, so Alice will raise this G, that means 17, to the power his secret number, her secret number. So 17 must be raised to the power 10.
a mod
Then
operation
a
needs to
mod
be done
operation needs
in
to be
mod
done,
13,
then mod 13,
mod 13.
mod
So the
13.
red things are
So the
already.
red things are already
So
public.
similarly, Bob
So
will do the
similarly,
same
Bob
thing.
will
So
do the
Bob
same thing.
will
So Bob
raise
will
17,
raise
and
17,
this 17
and this 17 should be raised to the power of
so
11.
17 to the
So
power
17
11.
to the power
Then
11.
rest of the part is
Then rest
mod.
of the part
So
is mod. So
mod
mod
13. So let
13.
us do the
So let
calculation
us
and
do the
find out.
calculation and find.
So we have these two
So we
numbers
have
as
these two
9 and
numbers
10.
as
So
9 and
Alice's
10. So
number
Alice's
was 9
number was 9
and Bob's number
and
was
Bob's
10.
number was 10.
So these two numbers
So
needs
these
to
two
be
numbers
exchanged.
needs to be
So now
exchanged. So
Alice
now
will send
Alice
this
will
number to
send
Bob.
this number to Bob.
So this 9
So this
will be
9
sent
will
to
be
Bob,
sent to Bob,
and this 10
and
will be
this
sent
10 will
to
be sent
Alice.
to
But
Alice.
since
But
in transit
since in
we
transit
crossed
we
the area
crossed
of
the
Eve, so
area
we
of
have to
Eve, so
assume
we
that
have to
these
assume
two
that
values are
these two
already
values are
known by
already
the
known by
hacker.
the
So
hacker.
9 and
So
10 were
9 and
already known,
10 were
and
already
they
known,
already
and
know
they
that
already
we
know that
have
we
performed this
have
kind of
performed this
operation.
kind of
So
operation.
this 10
So
was
this 10
generated by
was
using this
generated by
kind of
using this
operation,
kind of
but
operation,
evil
but
Eve,
evil
she
Eve,
doesn't know.
she doesn't know.
So by
So
using
by
this kind
using
of operation,
this kind of operation,
so evil Eve, she
so evil
doesn't know
Eve, she
which
doesn't know
value of
which value of
this
this
thing produce
thing produce
this number.
this number.
So 17
So
to the power what
17 to the power what
produce this, because there
produce
could be
this,
so many
because there could be
solutions.
so many solutions.
Similarly, we can
Similarly, we can
also say that this
also say
9,
that
even
this
though
9,
evil
even though
Eve knows
evil
that
Eve knows that
17 to the power
17 to the
something
power
mod
something
13
mod
gave 9,
13 gave
but she
9,
doesn't
but
know
she
the
doesn't
secret
know
number
the
that
secret
was
number that
generated by
was
Bob.
generated by
So
Bob. So
evil Eve
so
cannot
evil Eve
find
cannot
out the value of
find out
the
the
two
value of
values
the
of
two
x and
values
y.
of
These
x
two are
and
not
y.
known.
These two are not
Even though
known.
these
Even
numbers are
though
called
these
a and
numbers are
b,
called A
this
and
a and
B,
b are
these A
known.
and B
So
are known. So
this is b,
this is B,
and this is
and
capital
this is
A.
capital
So
A.
even though these
So
two
even
values are
though these
known,
two
so
values are
this doesn't
known,
mean
so this
anything.
doesn't mean
So this
anything.
doesn't mean
So this
anything.
doesn't
So
mean anything.
because of
So
this reason,
because of this reason,
it doesn't
it doesn't
the hacker will not
the hacker
be
will
able
not
to
be
decrypt the
able to
message.
decrypt
So
the
this is
message.
A
So
and
this
that
is
is
A
B.
and that is B.
Similarly, we have to
Similarly,
now
we have to
do the
now
rest of the
do the
operation
rest
to
of the
find out
operation to
find out the key value of
find
the
out
key.
the key value of the
So
key. So Bob will,
Now
Alice
raise
will
this
now
10
raise
to the
this
power
10
again
to the
his
power
secret
again,
number,
his
which is
secret
to the
number,
power
which
10.
is to the
So
power
10
10.
to the
So
power
10
10,
to the
once
power
again mod
10, once
13
again
will be
mod
done,
13 will
and
be
it
done,
will give us
and
some
it
value.
will give us some value.
And on the Bob
And
side,
on
Bob
the
will do
Bob
the
side,
same
Bob
thing.
will do the
9
same
should be
thing.
raised
9
to
should be
the
raised
power
to
his
the
secret
power
numbers,
his
so 9
secret
to the power
number, so
11,
9 to the power
and
11,
do
and
the mod
do
operation,
the
so
mod
it will
operation,
give us
so it
something.
will
So
give
let's
us
see how
something.
much
So
it
let's
does.
see how much it does.
So we see that
So
both
we
of
see
these
that
two
both of
operations are
these two
giving us the
operations are
same
giving
number.
us the
So
same number.
we can call it
So
this
we
is
can
our
call it
final
this
key.
is our final
So
key.
this is
So
3,
this is 3,
and this number
and
is
this
also
number
3.
is also 3.
So in the
So in
example,
the
it was saying
example,
as
it was
K1
saying as
and K2.
K1 and
So if this
K2.
is
So
K2,
if this is K2,
this one can be
this
called
one
as
can be
K1.
called as K1.
So sorry for
So
this
sorry for
interruption.
this interruption. So
So now we see
so
that
now
K1
we see
is
that
equals to
K1 is
K2.
equals to K2.
So K1
So
is equals
K1
to
is
K2.
equals to
This means
K2.
that
This means
without
that
even meeting,
without
Alice
even
and Bob
meeting,
has
Alice and
managed to
Bob has
establish
managed to
a
establish a
secret
key,
number,
a
which is
secret
3.
number, which
On
is
both
3.
sides we have
On
the
both
same
sides,
number
we have
3.
the same
But
number
evil
3.
Eve
But Evil Eve
will
will
not be
again
able
will not
to
be able
perform
to
this
perform
operation.
this
He will
operation.
not be
He
able
will not
to
be
find
able
the
to
value of
find the
this
value
number,
of this
because
number, because
he
it
doesn't
doesn't know,
know the
he doesn't
value
know
of
the value of
this secret
this
thing. So
secret
this
thing.
is the ultimate
So this is
secret.
the
Now why
ultimate
is
secret.
that
Now, why
difficult?
is that
Let us
difficult?
discuss that
Let us
thing.
discuss that thing.
So there are three
So
hard
there are
problems
three
that are
hard
the
problems
basis of
that are the
cryptography.
basis
The
of
one is
cryptography. The
integer
one is
factorization,
integer
that means prime
factorization, that means
factorization.
prime
The other
factorization.
one is
The other one is discrete logarithm problem. The last one is elliptic curve. So today we'll not discuss the ECC by elliptic curve cryptography today. So we should discuss only integer prime factorization and discrete logarithm problem only. So now integer factorization is quite easy to understand. So imagine we have two large prime numbers. So for example, 1, 3, 7. I don't know if it is a prime or not. And if you are given another prime number, let us say 17. Now it's easy to calculate this result, which is whatever the value is, 137 multiplied by 137 multiplied by 17. It's 2329. So it's 2329. Now it's quite easy to calculate this value. Now imagine this 2329 is given, but you are asked you were asked to calculate or to find out the very specific two prime numbers. These two products of these two prime numbers will produce this 2329. Now you have to find out these two values. This is quite difficult to find because it will take a lot of time for the computer to find out this value. The complexity will go high. So this is one hard problem. We call it it's a one-way function, because to go from left side to the right side, it's quite easy. So it's quite easy to, if we know P and Q, it's quite easy to calculate this multiplication. But if we know this value, then we have to calculate the values of P and Q. That means reversing this operation, it should be hard. It is actually hard problem. So that is why the first basis of cryptography is called integer factorization by prime factorization. The second problem is called discrete logarithm problem. For this, we need to think about a clock for modular arithmetic. So imagine we have a clock. So in this clock, we have 12, how do you call it? 12 cells. So we can call this 1 o'clock as 13. So this is 13, and 2 o'clock can be written as this is 14 o'clock in the 24-hour time, right? This is 15, this is 16, and 17, and this is 18 o'clock, and so on. So basically, what we are doing is that we are putting a limit on 12, and after that, we try to take the mod of this value. So if we take the mod of 12, so 13 mod 12, which will give us this value 1. Similarly, if we take 14 mod 12, so this will also give 2. So 15 mod 12 will give us 3. So 16 mod 12 will be giving us 7, and 18 mod 12 will give us 6. Sorry. So I don't know whatever I told. So 15 mod 12 is 3. 16 mod 12 is 4, and so on. In this fashion, we can find out the values. But we see that if we are in the second lap, let's say we rotated once, now we are in 13, now we have rotated twice, so we are in the third lap, let's say. So 17, 18, 19, sorry, 17, 18, 19. After that, we will be reaching at 24, right? So 24. So this 13 can be written as for 25. So let me write it in a different color. So 13 will be written as 25. So we can write it 25. Then this is 26. This is 27. This is 28. This one is 29, and so on. But here, once again, we can do the mod operation and get the new value. Let us see what is the new value. So the new value is 24 mod 12 is, once again, this is 1. Similarly, if we do the mod 12 operation for all other values, so mod 12, mod 12, mod 12, and mod 12, we see that the original values will come back. So 26 mod 12 is 2, 27 mod 12 is 3. We see that this is
28
So
is
28
4 and
is
5.
4 and 5.
So we see that
So we
different
see that different
values of
values
the
of
same
the
thing
same
is
thing
producing the same
is
value. So
producing the same
let
value.
us,
So let us,
for the sake of
for the
simplicity,
sake of
let us forget
simplicity, let us
some of
forget
the
some of
values
the
and keep
values and keep
this only.
this only.
So we
So
understand
we
that
understand
if we
that
are in the
if
third
we are
lab,
in the
we
third
can
lab,
have
we can have
36 over here.
36
So
over
it
here.
will be
So it will be
37,
37,
38. So once
38.
again, we
So
will have
once again, we will
39.
have 39.
Then mod 12
Then mod 12
will give us
will give
once
us
again 3.
once again 3.
Then we can extend
Then we
even
can
further.
extend
The
even
next one will
further. The
be
next one will be
49.
49.
Next one will be, sorry,
Next one will be,
48.
sorry, 48.
Then 49,
Then 49,
50,
50,
then 51.
then
So
51.
eventually we
So
will have
eventually we
51.
will have
It will
51.
give
It will
us
give us
51. Then
51.
mod 12.
Then mod
So the
12.
mod 12
So the
will give
mod
us
12 will
once
give
again
us
the
once
this mod
again the
12
this
operation.
mod 12
This will
operation.
give us once
This will
again
give
3.
us once again 3.
Now let us
Now,
think that what
let us
happened
think
in
that
the
what happened
Diffie-Hellman
in the
key exchange.
Diffie-Hellman key exchange.
So we
So
created
we
something like
created
g to the
something
power
like g
x
to the
mod
power
n.
x
So
mod n.
we did
So
what?
we
We
did
did
what?
this
We did
operation. So
this
we did
operation.
g.
So we
This
did g.
17 was
This
g.
17 was g.
Then this
Then
thing was
this
x.
thing
So we
was
got
x.
g to
So
the
we
power
got g to
x.
the power
Then
x.
once again we
Then
have
once
mod.
again we
Then
have
13
mod. Then
was called
13
n.
was called
So g to
n.
the power
So
x
g to
mod
the
n.
power x mod
So
n.
we do
So
this
we
kind of
do this
operation over
kind of
here.
operation over here.
So we see that
We see that
this if this
this
3
if
is
this
known
3 is
by
known
hacker,
by
okay,
hacker, okay,
so 3 is known
so
by
3
hacker.
is known by
Now
hacker.
mod
Now mod
12, it is also known
12,
by
it
the
is
hacker.
also known by
The
the hacker.
generated
The
g,
generated G,
okay, the generated
okay,
g
the generated
can
G
also be
can
known by the
also be
hacker, no
known by the
problem,
hacker, no
g.
problem,
But
G,
to the
but
power what?
to the power
This
what?
is the secret.
This is the
So
secret.
we see that
So we
g
see
is
that G
always
is
raised to the
always
power that
raised to the
secret
power
number.
that secret
So
number.
anything is
So anything
raised to the
is
power that
raised to the
secret
power
number,
that
it is
secret
quite
number.
difficult
It
for
is
the
quite
hacker to
difficult
find
for
it
the
out.
hacker to
So
find it out.
17 to the
So
power what?
17 to the power
There
what?
could be multiple
There could be
solutions.
multiple
So even if we
solutions.
know
So
that the
even if
value
we
is
know that the
3,
value
so
is
the
3, so
possible
the
value
possible
of
value
sorry, once again,
once again.
so the possible
So the
values are
possible values
15.
are
So
15.
we can take
So we
all
can take
possible values
all
from here.
possible
So
values from
possible
here.
values
So
are
possible
15.
values are 15.
G to the power x
G
can
to the
be
power x
15,
can be
or
15,
it can be
or it can
27,
be
or
27,
it can be
or it can
39,
be
or
39,
it can be
or it can
51,
be
and the
51,
possibilities are
and the
endless. So
possibilities are endless.
any
So any
of these values or
of these
the future
values or
values
the
could
future
be
values
the
could be
actual
the
value of
actual value of
could be the actual
could be
value
the
of
actual
the
value
secret.
of the
So
secret.
we have
So
no
we
way to
have no
find that
way
out.
to find that out.
Even if we try to
Even
find
if
it
we
out,
try
we
to
need
find
to
it out,
find
we
out
need
the
to
value.
find out the
This is
value.
actually g
This
to the
is
power
actually g
x,
to the
right?
power x,
So
right?
this, even
So
if g
this,
is
even
known,
if
so
g is known,
g
so
was
g was
13 or 18, I
13
forgot.
or 18, I
G is
forgot.
17.
G
So
is
even if
17. So
g
even
is
if
known, so
g is known,
17 to
so
the power
17
what
to the power
is
what
creating this thing.
is creating this
So
thing.
it's quite
So
difficult to
it's quite
understand
difficult
because
to
of there are
understand
lots of
because of
values.
there are
So the
lots of
actual
values. So
secret
the
is how
actual
many times
secret
we
is
have
how many
rotated
times we
around the
have
clock.
rotated around
So
the
the
clock.
secret is
So the
to the
secret is
power
to the
what?
power
So
what?
to the power
So
what
to the
means how
power
many
what
times we
means
have
how many
rotated
times we have
around the clock.
rotated
So
around the clock.
if we have
So if
rotated
we have
once,
rotated once,
if we have rotated
if we
once,
have
the
rotated
secret is
once, the
15.
secret is
If we
15.
have rotated
If we have
twice,
rotated twice,
the secret
the
is
secret
27.
is
If we
27.
have rotated
If we have
thrice, the
rotated
secret
thrice,
is,
the
let's say,
secret is,
39,
let's say,
then 51,
39,
and so
then
on. If we
51, and
rotate
so on. If we
multiple times,
rotate
let's say
multiple
1000
times, let's say
times,
1000
then we will
times,
have some
then we
different
will have
value
some
of
different value
this.
of
But
this.
still,
But
the
still,
modulus
the
result will be
modulus
3.
result will
So
be
this is
3.
why
So this
it's
is
quite
why
difficult
it's
to
quite
find out.
difficult
So this
to
is the
find out. So this
discrete
is the
part of the thing.
discrete part
So
of the thing.
discrete,
So
we made it
discrete,
discrete
we
by
made it discrete
introducing
by
the mod.
introducing
And
the
why it
mod.
is the
And why
logarithm
it what is the logarithm problem?
if we
Because
want to
if
find
we
out the
want to
value
find
of,
out the
let's say,
value of, let's
17
say,
to the power
17 to the
x
power x
is equals to,
is equals to,
let's say, 15.
let's say, 15.
Now to calculate the
Now,
value
to
of
calculate
x,
the
we need
value of
logarithm.
x, we
So
need
x
logarithm. So
log
x log
17 is
17
equals to
is
log
equals to
15.
log 15.
কই গেল, হারাই গেল।
হয়ে গেল, হারাই গেল।
So overall
So
x will
overall
be
x will be
log
log
15
15
divided by log
divided by
17.
log
So this is the
17. So
logarithm
this is the
problem,
logarithm
but
problem,
we
but
make it
we
a
make it
bit
a
difficult
bit
because we
difficult
mix it up
because
with
we mix it up with
discrete things. So
discrete
we
things.
made it
So we
discrete
made it
logarithm
discrete
problem.
logarithm
So by
problem.
making
So
it
by
discrete,
making it
how do we
discrete,
made it
how
discrete?
do we
We
made it
added a
discrete? We
mod
added
something
a
over
mod
here.
something over here.
So mod
So mod
whatever, this
whatever,
will not
this
produce
will
any
not
fraction.
produce any
Now we
fraction.
have created it
Now we
even
have
further,
created it
we have
even further.
complicated
We
it
have
even further,
complicated it
because
even
in
further because
Diffie-Hellman key
in
exchange we
Diffie-Hellman
see
key
that
exchange, we see that
the numbers that
the
is being
numbers that is
exchanged is
being
g to the
exchanged is
power
g to the
Alice's
power
secret number,
Alice's secret
and on the
number,
left side we
and on
have
the
g
left
to the
side we
power
have
y,
g to the
Bob's
power y,
secret number.
Bob's secret
So
number. So
once again,
once
this,
again,
let's ignore the
this,
mod
let's
for
ignore
now.
the mod for
Okay,
now.
so this
Okay,
whole
so this
number
whole
is
number
raised
is
to the
raised
power Bob's
to the
secret
power
number
Bob's
when
secret
this one
number
is
when this one
exchanged.
is
So
exchanged.
this
So
one is
this
exchanged
one is
to Bob's side,
exchanged to Bob's
and
side,
this
and
part is
this
exchanged
part is
to Alice's
exchanged
side.
to
Okay,
Alice's side.
so
Okay,
right now,
so right now,
again this
again,
number will
this
be raised
number
to the
will be
power
raised
secret,
to the power
and this
secret,
number
and
will be
this
raised
number
to the
will be
power
raised
that
to the
secret.
power that
So
secret.
this will be
So this will be
sorry
sorry.
so
So
this thing will be
this
raised to
thing
the
will be
power that
raised to the
secret.
power that
So we
secret.
understand
So
that
we
these two
understand
will
that
be
these
equal.
two will be
G to
equal.
the power
G
x
to
to
the
the power
power
y
x to the
is
power y
actually,
is
so
actually,
g to the
so
power
g to the
y.
power
So
y.
this whole
So
thing
this
to the
whole
power
thing to the
x
power
is
x
actually
is
g to the
actually
power
g to the
x.
power
This whole
x.
thing
This
is to
whole
the power
thing
y.
is to the power
But
y. But
for modular
for
arithmetic, we
modular
have
arithmetic,
introduced
we have
mod in
introduced
between.
mod in between.
So
So
mod n.
mod
So
n.
on the both
So
side we
on the
will
both
have
side we will
mod
have
n.
mod n.
So on the
So on
left hand
the
side and the right
left
hand
hand
side,
side
we
and the
can
right
once
hand side,
again
we can
add that
once
mod
again
n
add
part.
that
It
mod
doesn't
n
harm
part. It
the
doesn't
equation.
harm the
So
equation.
we can have
So we can have
mod n.
mod n.
So simply we
So
have
simply we
exchanged
have
these two numbers,
exchanged
and
these two
eventually
numbers,
we
and
have the
eventually
mod
we have
n
the
over
mod
here
n over here
and this mod
and this mod
n over there. So
n over
eventually
there.
we
So
see that these
eventually
two
we see
numbers
that
are
these two
exactly the
numbers are
same,
exactly the
because let's say
same,
2
because let's
to
say
the power
2
3
to the power 3
to the power 5
to the power
is
5
actually
is
2
actually
to the power
2
5
to the power
to the
5
power 3.
to the
So
power
because
3.
of this
So
thing,
because of this
it's quite
thing, it's
easy
quite
to
easy
calculate,
to
to come up with the
calculate,
same
to come
number,
up with the
but
same
for
number,
the hacker
but
it's
for
quite
the hacker,
difficult
it's
to
quite
guess
difficult
the
to
value
guess the
of
value
x,
the
the
of
secret
x,
number
the
x,
secret
or the
number
secret
x,
number
or the
y.
secret number
So
y.
for
So
discrete
for
logarithm
discrete
problem
logarithm
and the
problem
integer
and the
factorization
integer
problem,
factorization problem, we have
we have covered
we
both.
have
We have
covered
covered
both.
both
We have
in
covered both
Diffie-Hellman key
in
exchange. So this
Diffie-Hellman
is
key
why
exchange. So this
Diffie-Hellman
is
key
why
exchange
Diffie-Hellman
really
key
works.
exchange really
But
works.
there are some
But
problems
there are
with
some problems with
Diffie-Hellman key exchange,
Diffie-Hellman key
as
exchange,
it
as
was discussed
it
in the
was
book of
discussed in the book
Christoph
of
Parr.
Christoph Parr.
So
So
in Diffie-Hellman key
in
exchange, there is a
Diffie-Hellman key
problem.
exchange, there is a
That means
problem.
the
That means the
first, if the
first,
symmet
if the symmet
sorry,
sorry
sorry, we see that
sorry, we
for
see that
Diffie-Hellman,
for
its
Diffie-Hellman, its
secret key is
secret key
established
is
with the same key.
established with the
Okay,
same key.
so
Okay,
for
so
Diffie-Hellman,
for
the
Diffie-Hellman,
secret key
the
must be
secret key
transported
must be
securely. So
transported
that means
securely. So that
Alice and
means
Bob must
Alice and Bob must
meet in a
meet
secret
in
place.
a
But we
secret place.
understand that
But we understand
Diffie-Hellman
that
solved this problem.
Diffie-Hellman solved this
The another
problem.
problem
The another problem
is not actually a
is
problem of
not actually a
Diffie-Hellman,
problem
but a
of
problem of
Diffie-Hellman, but a
symmetric
problem of
cryptography.
symmetric
Is that the
cryptography.
key
Is that
management
the
problem?
key
Because
management problem? Because
these keys,
these
when the number
keys,
of
when
user
the number
grows,
of
the
user
key
grows,
size
the
is
key
n into
size
n
is
minus
n
1
into n
divided by
minus
2.
1
So
divided
we
by 2.
understand that
So we
for
understand
100
that for
users,
100
the
users,
number of
so the
keys
number
would
of
be
keys
100
would be
multiplied by
100
99.
multiplied
So
by 99.
100
So 100
multiplied by
multiplied by 99 divided by 2. So to managing this many amount of keys, this is very hard. So 50 multiplied by 99 is a very large number. So 50 multiplied by 99 is 4950. So 4950 number of keys needs to be stored in the database, in the system's database, in order to make a symmetric key to work. And the biggest problem is non-repudiation or accountability. We understand that if both parties, Alice and Bob, have the same key, now anyone can encrypt the message and say that I didn't do it, Bob did it. So since Alice and Bob have the same key, so encryption will always happen with the same key. Now, any encryption can be done with the same key from the Bob side as well. So by using a different message, message 2, now it is quite difficult to understand who sent this message because both of them are using the same key. So they can deny or they can repudiation. They can do this repudiation. So that they cannot do this repudiation thing, we call it, this is non-repudiation or accountability. So this is the problems of symmetric key cryptography. The one is key establishment, the other one is key management. Key establishment is solved with Diffie-Hellman, but the key management remains the problem. Another problem is man in the middle attack. It can be done. So imagine we have a Diffie-Hellman key just like before. So let me take a fresh copy. So imagine we have a Diffie-Hellman key before. So right now, Evil Eve cannot decrypt this message. But Evil Eve did an evil plan. He established that he came to Alice and said that, hi, I'm Bob. Actually, he's not Bob. He's actually fake Bob. So this is a fake Bob. And by presenting himself as Bob, so Evil Eve can establish a key between Alice and Eve, saying that he is actually Bob. So here they will perform Diffie-Hellman and exchange or agree upon a key, and that can be used to decrypt the ciphertext. Because Alice is thinking that he is sending the message to Bob, but it is not actual Bob, it is the fake Bob. So for this, this key 1, let's call it key 1. So with this key 1, they can decrypt the message. Now, when the message is being sent to Bob, he can also establish a Diffie-Hellman key with Bob. So let's call this key as key 2. So here also between Bob and Eve, they will establish a key. So this key will be called key 2. And previously they have established another key between them. This key used to be called key 1. So we see that this first part of the communication is encrypted with key 1, but this key 1 is known by hacker. This key 1 is known by hacker, so this message can be decrypted. Similarly, in the second part of the system, we see that Evil Eve presented herself as Alice, which is actually the fake Alice. So he went to Bob and said that, hi, my name is Alice. But actually he is not Alice. So here he will create another Diffie-Hellman key, which is called key 2. So now this part of the communication, so Evil Eve will once again perform the encryption operation once again, but this time with the new key. So Evil Eve will perform the encryption operation. So instead of decryption, he will perform the encryption operation, but this time not with the previous key, but it will encrypt the message with the new key. So that means the key between Eve and Bob. So this key is key 2, and it will produce a new ciphertext C1. So this new ciphertext is C1. So C1, now C1 will be sent to Bob. Now Bob thinks that he received the message from Alice, so he will try to decrypt this C1. So it will put it in the decryption function. And since he thinks that key 2 is the secret key between himself and Alice, so he will try to find the message in between, and we see that the original message M is back. So the confidentiality is still lost. The confidentiality is still lost. Confidentiality is gone. So we see that without this thing happened because of this thing, this vulnerability, that somebody came here and claimed himself as Bob, and Alice believed him. And also for this one, Evil Eve came to Bob and said, "My name is Alice." So Bob believed him and performed in Diffie Hellman. So Diffie Hellman should not be played with unknown people. Diffie Hellman should not be performed with unknown people. Diffie Hellman needs to be done with known people. So in order to identify, in order to authenticate a person, we need asymmetric key cryptography. That means symmetric key is no longer working for us. But symmetric key is still faster than asymmetric. So that is why symmetric key is used for every session. In practice, we use symmetric and asymmetric cryptography both. So first we authenticate each other with asymmetric cryptography. Then after that, the next of rest of the communication is transferred with Diffie-Hellman with the session key, and this session key is used to encrypt the rest of the communication. So this kind of attack that has been demonstrated over here is, once again, we have the release of message content, release of message content. That means our secrecy or confidentiality is lost. Our confidentiality is gone. That means the message is gone. And this kind of attack is also known as
এখন
MITM,
সময়
or
রাত
man
12টা
in the
30 মিনিট।
middle attack. Man in the middle attack. So in this man in the middle attack, they did not modify the message. They just perform a passive attack. That means they did not modify the message. They just opened the message and decrypt the message, then encrypted it once again. So the release of message content was performed by Evil Eve. So in practice, what do we do? So in practice, we use a combination of both symmetric and asymmetric cryptography. So in asymmetric encryption, we have a pair of keys instead of one key. So each user will have a public key and a private key. So these two are mathematically linked. So if we encrypt one message with a private key, we need the corresponding pair of public key to decrypt the message. Similarly, if we encrypt something with a public key, we need the corresponding pair of private key to decrypt the message. So for this thing, let us say Alice want to send a message M to Bob. So this message M needs to be sent to Bob, but we know that Evil Eve is listening to it. So right now, what we can do is Bob can send his private key to Alice, public key to Alice, and Alice can use this key to encrypt the message M that is to be sent to Bob. So here we can simply perform the encryption operation on this side. So Alice will perform the encryption operation. So this will be a comma and encryption operation, and it will produce a ciphertext C. So this C can be transported over to the hacker first, then to Bob. So Bob will receive a copy of C and Evil Eve will receive a copy of C. Now on the Bob side, Bob can perform the decryption operation. So decryption of this ciphertext C, and the corresponding pair will be required to decrypt that key. So here here the key is the corresponding pair. So the public key was used, so the private key needs to be there for the decryption. So the private key decryption with this private key will reveal the message M from this one. So evil Eve will not be able to perform this operation because the knowledge of the private key is not private key of Bob is not known to evil Eve. So evil Eve will not be able to perform this operation. So this will ensure the secrecy between them. Now what we can do, we can, instead of this message M, what we can do, we can transport the key instead. So what instead of the message, let us transport the key. So here the ciphertext C will be generated just like before. So but instead of the message, so now this key will be produced from the decryption operation. So now we see that this key has been established between Alice and Bob, but still evil Eve cannot find the key. He still only knows the C and the new C and the old C. It doesn't really matter. Now after that, now after that, rest of the communication will be done using symmetric encryption, not asymmetric, because this operation is computationally expensive. Asymmetric cryptography or asymmetric encryption decryption is expensive. So for this reason, rest of the communication will be done using asymmetric key. So the actual message will be communicated with the key that has been transported earlier to produce the ciphertext. Let's call it C3, and this C3 will be decrypted by the same key that was transported earlier, and this is decryption operation. So we will have our original message M back. So we see that this is a hybrid protocol. So here the initial communication was done with asymmetric encryption, and the rest of the communication for the session until the user logs out or the session ends can be encrypted by using the secret key. So the symmetric key. So the symmetric key algorithm is faster and the asymmetric key algorithm is a bit slower. We will discuss further when we get into the class. And the asymmetric key algorithm is called the RSA algorithm. We will discuss later. Thank you. Assalamu alaikum.